Okay, this is the video for question 1 on the Thevenin Norton homework. So here we are, we've got a circuit and we've got resistors R1 through R4, we've got a voltage source, we've got a current source, and the first thing you've usually got to do with these is figure out which one is the reference. And here you'll notice that we don't actually have a value for well, which one is the load, and we don't have a value for R3. So in this case, the load resistance is R3. That's this one here. Okay, so let's have a look. Remember, there's three ways we can figure out the Thevenin voltage. There is, the Thevenin resistance. There's the equivalent resistance technique. There is the open circuit voltage, short circuit current technique, and there's the apply a voltage technique. This one, the problems with constraints on each of those. The first one, the equivalent resistance technique, we need to make sure there are no dependent sources, and in fact there are no dependent sources, so that's the one I'm going to use. So let's see what that does. So the equivalent resistance technique says that you remove the load resistor, so remove R3, and then we replace the independent sources, Vs and Is, with their ideals. So replacing Vs with its ideal will give us a short or a wire, and then we're just left with R1 and R2 on this side, and then on the other side we replace Is with its ideal, which is an open circuit, because current sources are just open circuits when we set their value to 0. So then we're left with R1, which is 2 ohms, R2, which is 7 ohms, and R4, which is 4 ohms. And we just want to see what the equivalent resistance is here, and I think you should be able to see that that's going to be 4 ohms in series with the 2 in parallel with 7. So it's going to be 4 plus 2 in parallel with 7. So let's see if we can do that in MATLAB. Wherever MATLAB got to, there it is. Let's just make a new thing, and this is save that as homework 5 Q1, right? And our equivalent is going to be 4 plus 1 on 2 plus 1 on 7. 1 on 7. Okay, and that tells us it's 5.556 ohms, and that's the answer I got in here. And then the Thevenin voltage, unfortunately there's not an easy way to get that, right? What we have to do is we have to figure out the open circuit voltage. And so the open circuit voltage on this side, let's just label that as point A and this is point B. So VA equals, and this is just a voltage divider, it's not connected anywhere here. Remember, we've removed R3. So R1 and R2 is just a voltage divider, so it's going to be 7 divided by 7 plus 2 times Vs, which is 100. And we can put that into MATLAB 2, and we'll just call that VA. VA equals 7 on 9 times 100. Right, and what does that give us? That's 77.78 to 4 significant figures, 77.78 volts. And then the VB is just going to be, the only thing happening on the other side of the circuit is that IS is going straight into R4. R4 is 4 ohms, and the current is 6 ohms, so that's just going to be 24 volts. Okay, and then the output voltage, or the Thevenin voltage, the open circuit voltage, is going to be VB minus VA, and so that's 24 minus 77.78, and that should give us our minus 53.78 volts. Okay, now the next part, maximum power. Remember, maximum power transfer theorem says that the load impedance has to equal the Thevenin resistance. So we just copy RTH into that, and that should tell us what it is. And then the maximum power dissipated by the load. So remember, now what we've got is we've got a VTH, and we've got our RTH, and at maximum power dissipation we've got another RTH, right? So our current is going to be VTH on 2 RTH, right? So our power is going to be now, I think it's easiest if we just do the power as I squared RTH. We could do it, figure out what the voltage here is, right? And then just do V out times I, but we've already got I, so we could just do P equals I squared RTH, so that's going to be I squared is V squared TH on 4 RTH, because the RTH is cancelled. So that's going to be, so let's just put that VB in here. VB equals 24, and VTH equals VB minus VA. Let's just check that that gives us the right answer. Right, minus 53, looks good. And then our power is going to be VTH times VTH on 4 on R equivalent, or RTH. And let's see what that gives us. And that gives us 130.1, and that's going to be watts, right? So 130.1 watts. And that is question 1 done. Oops, I should have done that, and I'll just write it down as 130.1 watts. Okay, another video coming up for question 2.